All right, recording and rolling. It is Thursday, January 11th. So today's mostly going to be a demo day. I got a couple live demos for you guys, a bunch of video demos related to harmonic motion, waves, and if we have time, some textbook puzzles. All right, so I was looking at you guys' AP Classroom. You guys know this due, well, by the time you guys walk in on Tuesday morning, we're going to a 3-day weekend pretty soon. I know last couple of days been a little bit crazy with the schedule, so I want to make sure that you get all the information you need to be able to do this. I think you guys will be able to figure this out. A lot of the questions looks like were related to stuff from last semester. There are quite a few conservation of energy questions. Okay.
This is a C class or this table?
This is AP Classroom. AP Classroom. Yeah.
I don't know, half semester.
Yeah. Yeah. Okay. So go to AP Classroom. There's a Unit 6 open, right? And then on Tuesday we'll go over the solutions, right? Right. So here's a quick snapshot of. I think what's on this page is all you need to answer all the questions. I missed a couple things, but I think this is it, right? So there's two basic kinds of oscillating scenarios, right? You got the pendulum, which you guys just did a lab on, right? And you got blocks and springs, which I do have a lab rigged up. So I mean, here's basic spring, attach lab light to it. It's gonna oscillate back and forth. One of the video demos I have today is an animation of this, so you guys see that, right? And there's two basic orientations. You can have a vertical or a horizontal orientation. Now, first time I was going through this myself, I was thinking, okay, well, if it was vertical, you maybe have to consider that there's weight or gravity field acting, whereas horizontal, maybe you wouldn't consider that. Right? It turns out that both of these have the exact same time period, which is just this right here. Time period for oscillating spring is 2 pi square root m on k, where m is the mass of the block attached to it, right? K is the spring constant, how stiff is it, right? Okay, so that's regardless of its orientation, okay? So even if it's oriented vertically, you don't have to consider gravity, anything like that, right? In fact, one of the questions specifically says, this phrase here says block spring system. Guys, if they say block spring system, what object are they leaving off that you might otherwise think to consider? The Earth, yeah. It doesn't say anything about the Earth, right? Block spring system, right? Right. So if they say that too, guys, if they say block spring system, and you want to say solve with a conservation of energy equation, right? Talking about a system, it's a good chance they're thinking about something to do with the energy being conserved. That's what this is right here. Sum of energy initially goes sum of energy final. Think, okay, well, here's maybe forms of mechanical energy I might want to consider for something like this, right? But here we got energy stored in spring, 1/2 kx squared. Kinetic energy, 1/2 mv squared. Gravitational potential energy, mgh. Right? Guys, if they're talking about a block spring system, which one of these do you not care about at all? Which one of these are you not going to even consider? MGH, yeah, right. Because height change, like relative to what if there's no Earth, and also if there's no Earth, there's no external gravitational force to yeah. So if they say block spring system, don't even write MGH. Don't even write that. You just maybe care about 1/2 kx squared. Now x could be how much it's stretched from equilibrium or how much it's compressed from equilibrium. Right? Either one of those, right? Right, and possibly 1/2 mv squared if it's in motion. Right? But if you're talking about some maximum stretch or some maximum compression, guys, at the maximum stretch or compression, is there any speed? No, because it's like turning around. In which case you don't have this either. Okay, right. So you can start something like that. Right. Speaking of 1/2 kx squared, that's related to Hooke's law. Hooke's law, I think, does show up a few times in your AP class, if I remember right. So F equals kx. Right. So how stiff is the spring K? How much do you stretch or compress it from equilibrium? That's x put together. That's the force required to do that. Right. Or if you slap on a negative sign, maybe the restoring force. Right. Right. And then if you accumulate the area under this curve, F versus x, you get 1/2 kx squared. Right. But you guys saw that last semester, so I think you guys can navigate that. So you guys good with that? Okay. Also, before we hit some demos, I've been going through posters last couple of days, and both my AP classes turned out that I didn't quite get to the last few. So we'll have these posters be a little bit different from. Right. So the last one you guys saw was this in the bell ring. Right. So the last few here. So you pluck a guitar string, starts oscillating. And maybe you want to tune it. So you turn the tuning peg to tighten it, and now you're going to hit a different note. And what's the physics behind that? Right. So the physics goes like this. Right. So whenever you pluck any string, I'm saying guitar string, but this could be piano string, this could be violin string. Right. It's going to go into this type motion. I see half of a wavelength here. Right. You guys are going to see this later on today. Right. We'll go over wavelengths. Right. This is like half the story. right? If you had well, if you double this, you get one full wavelength. So this is half wavelength. That's what this says right here. It says wavelength is twice the length of the string itself. Here's the full length of the string. If you double that, you get a wavelength, right? So you see some examples of that later, right? Here's the wave formula that I think flashed in front of you guys briefly the other day. Speed equals wavelength times frequency, right? Wavelength could be in meters, frequency could be in hertz, that's 1/seconds. Meters times 1/seconds, hey, that's meters per second. Oh, that could describe speed. Oh, we get this phone call. Pause the. All right, resume back here. All right, so now here's the speed of a wave on a string. It depends how tight is the string, that's the tension, right? But also this linear mass density, that's mass per unit length, right? Right. Okay, so you can have like some physical string has this physical property, some mass per length. When you're turning the tuning peg, okay, you're changing the tension, right? And this is how it all connects. So you're aiming for some musical note frequency. Here, just as an example, I got these tuning forks here, right? We'll do a lab probably next week that involves these tuning forks, right? It says how many hertz, right? How many hertz that corresponds to a musical note, right? That's like this frequency right here. You're aiming for some frequency, and as you turn the tuning peg, you change the tension, right? It all connects there if you want to know physics, right? We got, I've got a video demo that looks kind of like this. There's a oscillator that oscillates a string. You can oscillate it up and down and then create different standing waves. Yeah, so look for that later. I got a video demo. Right, so this ties back to music too. Give you guys a story of music here. Right. So back at thousands of years ago, back to Pythagoras' days, Pythagoras was walking around. I think the story goes he was listening to there were these I think these pot makers that were hammering these pots, different sizes, and he knows like there were certain pots that like sounded good together, right? And that was like harmonization. And so then he was like measuring what were the ratios of the diameters of these pots that eventually comes up with like some of the first music theory for how you make harmonization. Here, this could be like a major chord, right? Like root, major third, fifth, octave. Right? Okay, so what's the physics? The physics has to do with ratios of frequencies. Okay, so whenever you double the frequency, that's how musically you get the octave. Right? So one of the notes, like an A note, could be defined as 220 hertz, and if you double that, you get to 440 hertz. Right? So that'll be like the next A note, and then 880 hertz would be double that frequency. But what if you want to hit other notes in a chord? Okay? So fifth could be a 3:2 ratio, major third could be a 5:4 ratio. Right? Now this is like actually an old definition. This is one way to think of it. This sounds particularly good to your ear, but there are actually different type definitions for how to define different notes. Right? Now, if you listen to, say, Mozart play one of his pieces on a piano hundreds of years ago, it would sound different than it does today because they tuned instruments differently hundreds of years ago than they do today. Right? It used to be that if you switch keys, say from like C major to E major or something, right, it would actually sound different, had a different quality to it. Because if you're stuck within a key, then this sounds really good to your ear, like these ratios. And this is just a few of the notes, for example, right? Right. But once you switch keys, then well, now those aren't aligned to these frequency ratios won't be the same for all keys. It won't be universal. It's stuck for one key, right? Right. So it sounds a little different, right? And then they would have these table recommendations. Say if you want like really happy song or really like melancholic song or really this kind of song, then you want to pick particular keys to compose that song in or play that song in. Right? Now it's not true today because today instruments are tuned according to this green box down here called equal temperament. Now this is an actual exponential relationship, right? Which you don't see very often in this class, right? But you see here, right? Right. So in Western music, there's 12 different named notes where you cycle back to the next octave. So n is the number of half steps you could call this, right? Right. So let's see how close this is, how close this lines up. Let's say the major. Let's look at the fifth, right? So the fifth is 7 half notes up from a root note. So if you count like piano keys, right, including the black keys, you count up 7 half steps to get to the fifth, right? So if I plug in a 7 for this n, let's say we got what's 2 to the power of 7 out of 12, right? It says 1.498. That's extremely close to 1.5, right? Oh, that's what 3 to 2 is, right? It's like 1.5, right? Your ear probably cannot tell the difference between those two, so that works pretty good, right? But what about something like the major third? Right? It says 5-4 ratio. That's like 1.25. What does this say? So that's 4 half steps up. So if I put in 4 out of 12 here for that power, that's 1.2599. It's like 1.26. Okay, that's off a little bit. Your ear might actually be able to distinguish between this major third and this major third. It's two different definitions, right? They're so different. Right? So equal temperament, the sort of disadvantages that there is no unique sound for each key. They all sound kind of the same, but maybe that's kind of an advantage too, right? So you can have some composition, you can switch keys and it sort of sounds the same. So you don't really know what key you're in. It sort of sounds the same. Right? All right. Doppler effect. I got this one of the live demos I'm gonna do with you guys. Right. So you guys ever stand by the sidewalk, car goes by, it sounds like meow, meow. You hear a pitch shift, right? Now you don't hear the pitch shift if you're in the car. You just hear just the engine's a solid tone, right? If you're outside, you hear pitch shift. So what is the observed frequency compared to the source frequency? Right? And it has to do with what is the speed of sound, what's the speed of the observer, or I should say velocity of the observer. It could be running back and forth, and here's the velocity of the source could be also going back and forth. Right? So if it's headed towards you, you hear those. These might be like crests of waves, like high pressure points, because sound will be a pressure wave, right? Okay. They would reach you more frequently, and a higher frequency corresponds to a higher musical note, like a higher frequency, right? And then on the backside, you hear like a lower frequency, like less frequency, less frequently those wave crests. Right? Now the speed of the sound is the same everywhere, right? So maybe it's like could be about 340 meters per second, the speed of sound, like on Earth, right? Something like that. So that's the same. But like once that sound wave is released into the atmosphere, it just goes at whatever speed it goes for that particular medium, right? Something like that. So speed sounds whatever it is, right? But the frequency could sound different. Right? Now here I drew. Why do I make this blue and red? Because there is a related idea. There's a Doppler effect also for light, right? If you look at distant galaxies, most galaxies are moving away from us because of universal expansion, and what's called red shifted. So the light coming from them appears like more red than it would be if we were moving the well, if the galaxies weren't moving relative to us, right? Except for Andromeda Galaxy. Andromeda Galaxy is headed towards us, so it's actually blue shifted, right? So with light, you get red shifting, blue shifting. Right. What if you're going like faster than sound? Right? No, this one doesn't work for light because you can't go faster than light, but sound, yeah, you can go faster than sound. You guys ever hear something like Mach 2, Mach 3, Mach numbers, right? That tells you how fast you're going relative to the speed of sound, basically, right? So like if the jet's going Mach 2, it's going twice the speed of sound. Supersonic, faster than sound. Okay. And last poster here is how do you measure how loud the sound is, right? So probably heard decibels, right? So what's the math behind that? Right? Now this gets a bit involved. This is also a logarithmic scale. You could say exponential, right? Which remember, exponential you almost never ever see in this class. But here's a couple examples, right? We got equal temperament for musical notes, and here we got how loud is the sound, right? Okay, so this example, me talking right now is probably pretty close to 60 decibels, right? Like talking speed, 60 decibels, right? Now, what would it mean if I talked like twice as loud? Would that be 120 decibels? No, because this decibel has to do with like an exponent on an equation, right? If I talk twice as loud, that'd be actually pretty close to like 63 decibels is what it would be. So a good rule of thumb is every 3 decibels is approximately doubling the loudness. 120 decibels would be something like well, they call it threshold of pain, like about to tear your eardrums apart, right? So here I've got a logarithmic formulas up here, right? So decibel, right? So you guys know deci is 1/10 of something. It's a prefix we don't use too often in this class, but like 1/10 of a bell. So if you divide these numbers by 10, right, we got what 4 bells, 6 bells, 8 bells, something like that, right? So this is kind of like 10 to the power 6 here. Right? So if you went from 60 decibels to 120 decibels, that's like from 6 to 12 bells, right? Which is like double, or that's because isn't that, if it's 10 to the power of 6 versus 10 to the power of 12, isn't that 10 to, guys, what's 10 to the 12 divided by 10 to the 6? That would be 10 to the 6, right? And right, it's 12 minus 6 is 6, right? And what is 10 to the power 6? That's called a 1 million, 1 million. Right. So going from 60 decibels to 120 decibels is like, you can think of it like a million times as loud, right? So if they're like a million of me all talking to you at the same time, they go from here to here. Right. 0 decibels doesn't mean 0 sound. Like 10 to the power 0 is not 0. Right. So it's just extremely quiet. Right. Here's in terms of pressure or in terms of intensity. Okay. All right. There you go. There's the ones I didn't get to the other day. Okay. All right, so let's switch over and do some live demos I got for you guys. Before we do that, you guys got any questions so far? Okay. Okay. Yeah, make sure notes for your AP classroom can help you out. Okay. All right, I got a Slinky here. Slinky, really long Slinky. Okay. Now, if you're watching this video, you have to use your imagination a little bit. I'm gonna attach this to the doorknob, stretch this across the room, and set up some different kind of waves here. Okay. All right, here we go. So, like if I shake this up and down, let's get this a little tighter here. Shake this up and down, that could be like a transverse wave, right? So I'm like propagating energy across the room, right? It's gonna take some time, right? There's like a time delay for that energy to go across the room, right? And now Slinky, you can think of it like a spring with a really tiny spring constant, really low spring constant. If this was stiff, if this was like a log or something that was stiff, right? I push on one side and it looks like it immediately like pushes the door on the other side, but that's not really true. It's just the speed of sound, which is the speed it would travel, would be really fast through something solid like a log, but through a Slinky would be relatively slower. So you can actually see the wave pulse. Right? You can see the wave pulse going back and forth, right? What if, okay, that's kind of a transverse wave, right? What if I pluck it like this? Ooh, you guys see it racing back and forth, right? Now that's not transverse anymore. What's that called? Is that longitudinal, right? Where the individual particle motion and the propagation of the energy is all the same direction. That's longitudinal. Versus if I shake it up and down, it's like transverse, right? If I shake it up and down the right way, I might be able to get a standing wave. All right, I think it's pretty close. Yeah, do you guys see a node in the middle? You guys see a node right in the middle? Like if you touched it right in the middle, there's a point that's not moving, right? Wouldn't actually affect the wave, right? Right, so that's a standing wave right there. Do you guys see like one full S shape? Right? Could you guys call that one wavelength? Is that one full wavelength? Right? That's the shortest part that you could copy paste that next to itself, and it would be continue that wave. Okay. Versus, let me shake this a little differently. Okay. So let's do a transverse wave. What if I do like this? Okay. How many? Okay, so that's another standing wave. Right? There's two nodes, one at the doorknob and one at my hands. Okay. And there's an antinode right in the middle. Okay. How many wavelengths is that? That is half of a wavelength, right? It'd be like half the story, right? Half wavelength. Then if you had another one, that would complete one full wavelength. Okay. Another demo for you guys is got Doppler effect. Right, so I got this piezo and a battery installed. See on this puff ball. I don't know if this showed up in the video, but I should be able to hear in class. Right, you guys hear that tone? Right. Okay, right. It's a solid tone, right? Okay. Right. Now, here. Gonna get this going around. Oops, reconnect that. Here you go. Now, do you guys hear a pitch change here, going like up, down, up, down? Okay. Now, as it's going towards you, it should be going kind of up and it's going away kind of down. Yeah. Okay. Now, I'm at the center of the circle. What do you think I hear? Sure. Yeah, I just hear a solid tone, right? Right. And then everybody out there can hear a pitch shift, but differently depending on where you're sitting in the room. Everybody hears something a little different. Okay. Right. So that's an example of Doppler effect. There's a really good Paul Hewitt explanation that I want to play for you guys. Okay, so in time. So let's switch over to these video demos. and yeah, all right, and that one will show up in time. It'd be an example. So hold on until I do it. All right, here's that animation I was promising you guys for yeah, oscillating block on a spring, right? And then in phase space, be like a point going around a circle at constant speed, looking kind of thing. Right, here's animation of transverse versus longitudinal. So I just did this in class, right? Transverse longitudinal. If it's transverse, the individual points go up and down, wave propagation left to right. Longitudinal could be a pressure wave. Everything's in the same direction. So individual particle motion left to right, and then the wave, the energy propagation is also left to right. 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 I think this one I think I may have shown you this the other day too. Right. So constructive interference, you got two wave pulses. Right? As they cross, you get add amplitude. But then, yeah, the waves go ahead and those wave pulses go ahead and cross right through each other. Right. Versus if it's destructive interference. Destructive interference. Right. Similar idea. Right. So as they're crossing over, they exactly cancel out. Then those pulses just go ahead and cross through each other. Right. Also, interesting, if you watch the wave pulse like bounce off the end, it actually inverts upside down too. Right here, let's watch that again, because right? There's a bunch of little things going on. Right. Right. So yeah, you can watch the wave pulses cross right through each other. And then at the end, watch it will be reflected upside down. Did I tell you guys the example of noise canceling headphones? You tell that, right? Have you guys ever worn noise canceling headphones? Yeah, maybe, right? Right. So that's actually this, except it's with a sound wave, which is a compression wave, but it's the same principle, right? So what they'll do, you have to turn them on. It's like battery operated, right? Is the noise canceling headphones? They'll take the ambient sound from the world and they'll invert it. So like all the high, low pressure, they'll mix it with that sound, and then what gets pumped into your ears is just it's like when these pulses cross over each other. It's like, right, and then you hear nothing. Right, so let's cancel it. All right, let's look at different standing waves. Different standing waves. Right. So not all waves have to be standing waves, but they could be standing waves. And right, so see some examples here. Right. Right. You guys saw some in class. Right. See if you guys remember. Is how many wavelengths is that right there? Yeah, one, right? Because that could be one full S shape, right? That could be one. Right. How many wavelengths is that right there? Yeah, 1.5 or 3 halves. Yeah, right. And then how about right there? How many wavelengths? Ooh, 2, right? You see, 1, 2, right? 2 full wavelengths, right? And then let's go back to the beginning. Right. There, right there. How many wavelengths is that? Half a wavelength. Half a wavelength, right? So if you like pluck a string on an instrument, it'd be like half a wavelength. Right. Let's look at resonance. Resonance. All right, so this is called resonant frequency. Resonant frequency. If you hit the right pitch, and it has to do with like what is the circumference of that glass. If you can set up a standing wave that is a multiple of the circumference of that glass, right? Then it could amplify itself and it'll resonate. So it's called a resonant frequency. There's a similar principle to how your microwave oven works, right? If you know the width of the microwave oven and you know the length of a microwave, which might be about like 12 centimeters or something like that, right? And like what's the frequency? it could set up a standing wave, right? That's why you have a turntable in your microwave oven, because if it didn't have the turntable, think about how a standing wave would work. Okay, let's go back to standing waves here, right? Right. Let's say you have a standing wave set up in your microwave oven, looks something like that, right? Right. Then all these node points, right? There would be no energy put into those, right? So you get like really hot and cold like points and whatever you're trying to heat up, right? So if you have the turntable, then it's more like even heating, right? There might be like a cold point in the middle somewhere, something like that, right? But engineers have to consider something like this resonant frequency when they're designing structures, right? Because a lot of structures will have some associated resonant frequency. I remember when I was at University of Florida, one of the buildings they have is they call it the O Dome. It's this building with basketball court in it. They play NCAA basketball games there. And supposedly, what I was told by my engineering instructors was that when they were designing and building this thing, they realized that the resonant frequency of that particular structure was like 2 hertz. And there was all the engineers freaked out at that point. It's like, oh, we were gonna have like a bunch of people, so like go Gators, go Gators, go Gators, you know, like 10,000 fans. And what's going to happen to the whole building if you hit the resonant frequency of that structure? Yeah, like what happened to this glass, right? It could break down. Which there's a really type example of this. Is anybody here ROTC? Who's in ROTC? Is anybody, right? Or maybe okay, yeah, a couple guys, right? You might know this anyway. So in the military, you taught to like march and step, like left, right, left, right, left, right. And there's a few reasons for that. One reason is that you can more efficiently move large numbers of troops across bases if everybody's marching in step. But there is one place where you're told specifically to not march in step. Everybody's told specifically break step and do not march in step. And that's over a what? Over a bridge. Okay? Because if you hit the resonance frequency of a bridge, this could happen. It has happened in the past where large numbers of troops marching over a bridge actually collapses the bridge. Now, how much that had to do with just the weight versus this resonant frequency, I didn't, you know, who knows? But it has happened before, right? So you're told don't march and step over a bridge. Now, here's a famous example. Some of you guys might have seen this. This goes back to 1940. Called Tacoma Narrows Bridge. This is out in Washington State, right, on the West Coast. So they built this bridge, opening day, yay, right? Then they notice this thing bounces. It bounces up and down a little bit, which, you know, not really ideal, but the engineers are keeping an eye on it. It kind of bounces up and down. Say, okay, well, we'll keep an eye on it, make sure it's okay. It's no cracks forming, anything like that, right? But one day it goes into this type motion. So there's this huge crosswind that's keeps pumping energy into the bridge, right? And if you count the time period, I think it's like 5 seconds it takes to cycle back and forth, like 5 seconds, right? So guys, if it's 5 seconds time period to oscillate back and forth, then what's the frequency in hertz? Like 1/5, right? 1/5 hertz, right? So that'd be like 0.2 hertz, right? That could be the resonant frequency of that structure, right? And what do you think this bridge is made out of? Concrete and steel? Yeah, concrete and steel. So concrete steel bridge, right? Hit this resonant frequency of 0.2 hertz. Right. Now, oh yeah, there's an engineer. He parked his car out there. He's walking along that nodal line to check this out. He did get off before it collapsed though. So the engineer did anyway. Right, let's go to the end here. Of course, we don't really see our modern day cosplays doing doing like this, right? So one thing they had to figure out is like, why did that happen? Right? So they could avoid that ever happening again. And it's kind of a clue in that frame right there. So it's kind of hard to tell. I mean, this is from 1940, right? So it has to do with the structure on the side. Here, let's do a little bit of engineered here. So if you look at, say, the side, right, they have all these vertical girders, right, holding up, right? Because they would think, well, there's a bunch of cars going across the top, right? The cars, that's a pretty big weight, right? You have to hold a vertical force, right? And anything is vertically oriented, that'll maximize that possibility, right? But all these girders being vertically oriented, there's no like lateral support. Okay? So all they did to fix this, and all they did like after collapse, they just went back and said, okay, well the posts are fine. We can just like rebuild the road. Right? So they went in, they put in a truss system like this, right? So that it can handle not only vertical forces but also horizontal forces too, right? And so modern day bridges, you'll see like this truss system, and then you don't really run into that Tacoma Narrows scenario again. Okay. All right, let's see what else I got here. Let's look at earthquakes a little bit. Earthquakes. Okay. So, hey, that looks like a transverse wave and a longitudinal wave. Right, guess that. Right now, earthquake terminology is called S waves and P waves. Right? I've heard S could stand for shear. I've also heard S could stand for secondary, and P could be a pressure wave or primary. Right? And both those would be accurate, right? Because that is a shear motion and a pressure motion. But also the order that those waves hit you, because they travel at different speeds. The P waves actually travel faster, hit you first, I guess hence primary, right? If you're in an earthquake-prone zone, you feel that P wave hit, that's like a warning. You have maybe a few seconds to either get under a solid desk or like outside the building, something like that, before the S waves hit you. I think I showed you this the other day, but let's do this real fast, right? And so here's like a magnitude 9 quake that hit Japan a few years back. There's the P waves there. Now if you look at the water, doesn't really look like it's moving a whole lot. Right? But then the S waves hit. Let's zoom ahead a little bit. Yeah, all right. Then things get really excited, right? So different kind of wave. Right? Now, if you know the time delay between those two waves, and you know how fast each of those waves is traveling, you can put two and two together and figure out how far away the epicenter of an earthquake is. Right? So let's switch back over here. So look at you guys ever see a big old earthquake hits and then on the news will say, oh, it's a magnitude such quake, and they can locate the epicenter. Maybe it's like somewhere out in the middle of the Pacific. It's like, how would they know? Right? And so how they know is they got all these seismograph stations all over the world. Okay? You guys have probably seen this right there. Like there's this paper scrolling, right? And if you have it's like a pen, right, which is pretty large mass pen, and it's on a spring, right? And this paper's just scrolling all day, every day. And so this pen makes just a flat line, and normally it's not very exciting, right? Because nobody knows when the next earthquake is going to hit. It's a real mystery, right? So maybe in the future, maybe AI will figure out somehow how to predict earthquakes. But right now, it's like really hard to predict when the next earthquake is going to hit, right? So you get these flat, straight, boring lines all day, every day, right? Until an earthquake hits. Earthquake hits, the entire ground is shaking. But the fact this is a large mass with a lot of inertia on a spring, very little of that energy actually gets to this pin. So this pin is relatively stable. The entire world is moving around. And then on the paper, you get, looks maybe something like this, right? Like flat, 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 and then right? Something like this, and then pow, then something like this, right? And then, okay, here's your P waves, and here's your S waves, right? And again, like if you know the speeds that these waves are traveling, and you know this time delay, okay, so there's some time this happened, like this wave hit before this wave, right? You can figure out how far away the epicenter happened, right? Like if this was right on top of the epicenter, you wouldn't get any warning at all. It'd just be like, happy birthday. Now you get all these S waves. But if there's a time delay, right, you can figure out how far away it is. Then you have all these seismograph stations. So you've got a big old map here, right? Big old map. It's like north, south, east, west. Big old map we're looking at, right? We got a seismograph station here, and let's say here and here, right? This one says, well, we know the earthquake happened like so far away, like so let's say 50 kilometers, right? So you can make a 50-kilometer radius around this one, but we don't really know what direction exactly, right? So call up the station and say, well, it happened like 30 kilometers away from us, right? So you make a 30-kilometer radius circle around this guy, right? And then you call this guy up here. This guy says, oh, it was like 100 kilometers away from us. So that's like a big old circle, yeah, something like this, right? Then there's some place where all these lines are going to converge, and then that's how you can locate epicenter of an earthquake. Something like that. Okay. So we got for you guys. I think I was showing you. I showed you guys earthquake test, I think, the other day. Big old building on rollers, just like real size, right? Okay. Got little people walking in the background. Right. let's check out. Let's do this one. I want to show you guys. Right, so if you have an oscillator, right? So here's an oscillator on the left, right? And a string, it's tied to the right side, right? And then you're gonna get this thing. Where they start this thing? Okay, this thing oscillating, right? Okay. Right, so 5 hertz. Okay, great. So not super exciting, but what if we up that frequency? Ooh, that looks like a standing wave right there, right? Standing wave, right? So call that 11 hertz, right? Now that's a half a wavelength, right? So if you know the frequency and the wavelength, which would be double the length of string, right? You do. Speed is wavelength times frequency. You can figure out the speed that waves are going to travel on a string. Now that speed is the same regardless of how this is oscillating, right? The fact that it's a string, it's some tension, some linear mass density, right? There's some speed that the sound is going to travel on that string, right? AP used to ask that question, but they don't ask it anymore, so you won't be asked that question, right? Well, what if we up the frequency some more? Ooh, look, 22 hertz. Hey, that's double the frequency, right? Guys, how many wavelengths is that right there? That's one. One wavelength there, right? Let's up the frequency again. It's going up, up, up. So, ooh, right, when it hit 33 hertz. Now it sets up another standing wave. There's 1.5 wavelengths. Got 44 hertz, it's 2 wavelengths, right? So the number of standing waves, right, you can go up a half wavelength at a time. Just get that. So all right. Let's do Doppler effect. All right, so you guys heard Doppler effect earlier. Let's look at the explanation for that.
But now what the bug starts to do is the bug starts to jiggle up and down.
All right. Let's look at the supersonic version of this. So what if that bug was like traveling faster than the very ripples that was sending out? Wouldn't that create like a cone wave? Okay. And so here's some supersonic jets. That's the military jets here. And you can see um, like as they're moving, the air will condensate. Right. So you guys saw like a cone wave flash right there, right? Like that. Ooh, yeah. So it's kind of a shallow cone, right? In fact, the faster that jet's going, the sharper the cone's going to be, right? Like, I bet if you measure the geometry of that cone and you knew the speed of sound, you could do some math and you could figure um, like how fast the jet was going, right? Like how fast supersonic was going, right? Um, yeah, and if you are say like on the ground and that jet passes you, what is that? What does that sound like? What's that called when that cone wave hits you? It's called a I'm looking for a sonic boom, like sonic boom, right? Something like that. All right. Got some other cool ones here. I'll show you guys this funny way. It's called Rubens tube. Rubens tube. So this guy's gonna light some flames and then put a musical tone over this. All right. Ooh, you guys hear it? Sounds like a really flat type tone. I think it's called like a like a sine wave, right? Right. So setting up a standing wave. Now it's a standing sound wave, right? Which is like a pressure wave. So you guys think all the place the fire is being pushed down, it's like high pressure, high pressure, high pressure, and where it's being kind of vacuumed up, like low pressure, right? You guys think, right? Okay, and there's some like solid frequency, right? There's like again, it's like a really flat type sound. It doesn't really sound like a trumpet or a piano or guitar, right? Uh, what's the musical term for like difference between different instruments? Different instruments sound different because they have different what, like timbre, right? And the physics of timbre is that you get a bunch of small waves in addition to like the main frequency wave. Right? Now here is just main frequency wave. It sounds like really mechanical, right? Um, yeah, so you get this nice smooth, looks like a, well, I mean, if you just follow the flames, it looks like a transverse wave, right? That's caused by a longitudinal pressure wave in the air. That's what's causing that, right? What if he changes the frequency? He's going to do later on here. Now, if he increases the frequency, what's going to happen to the wavelength? It's going to get shorter. Let's see if that happens. Yeah, right. So you guys see the wavelength getting shorter, shorter, shorter with a higher frequency, right? But what's happening to the speed? Is the speed the same? Yeah, the speed of sound is just the speed of sound, right? So it doesn't matter what the musical note is, right? The speed of sound is the same for all those, probably pretty close to 340 meter per second, right? All right, so remember, speed is wavelength times frequency. So the higher the wavelength, the lower the frequency, or vice versa. Let's see here. All right, some sound waves there. All right. Okay, we only got like 3 minutes left. Well, all right. Let me see. Maybe I'll just find a video demo to close this out then. See what else I got here. Ooh, let's do. See, this one's pretty cool. Pendulum waves, starring Alan. So those are all individual pendulums, right? They're all individual, but you guys are about to see an emergent property. All right, when you guys see the DNA double helix right there, right, that is halfway through. And then everything that happens after that point, it's kind of like playing the first half of the video just in reverse, right? And then it's going to go back to the original state. So a bunch of individual pendulums. That's pretty cool. Since I got see about a minute class left here, let's look at Chladni plates. Chladni plates. Okay, so this guy's talking about resonance and frequencies, right? It's got these plates, right? You guys, great day. I'll see you on Friday.